For this MOP and how it is that we're going to validate and or verify it, we need to do a series of calculations that take into account the expenditure of not only the processing or the manufacturing, but the individual components and electromechanical components. The individual materials and the lengths and portions, the thicknesses and the widths of all types of materials have to be taken into consideration and placed against a bulk pricing as found in the current markets. For how it is that we're going to go about that, here is a series of steps that we're going to take in order to accomplish this verification. Step one would be to research each component in bulk and or specifically by pricing and availability in the current market as it stands via websites or by consumer locations or stores and such alike. Secondly, would be to research the individual manufacturing processes such as stamping, casting, molding, etc., and take them into account into the budget analysis process. Thirdly, would be to verify each component and process how it is that they carry themselves for when it comes to the application of taxes that might add a significant or which one of which would add a significant amount of tax dollar input or excess for each pricing and tally them up as the process continues. Fourth would be to adjust each process, each component, each individual metal component or electromechanical component to the current inflation rates as seen across the world or in the specific markets in which we are finding them. Fifth would be to simply just add everything all together. And sixth would be to finally compare to the target budget limit of 15,000 and see how it is of how much of the budget consumption has been used up. And this is how we are going to primordially be calculating and verifying our budget MOP.
And good afternoon. To actually explain now, the second MOP will be the maximum dimension area, which should be less than 5 feet by 4.5 feet. To validate this specific MOP, we decided to take the procedure using the tools of the CAD drawings and SolidWorks simulations, mainly the initial drawings that we did presented in phase C2. First, we'll be verifying the dimensions, the length, width, and height as the drawings in the models that I specify in the picture right here. In the end, we'll get the final result. We'll write the results and show the SolidWorks model will be the other presentation we have in the image next to the table. Mainly to validate this procedure, we actually needed to take multiple steps in the assembly. And initially, we thought it would be actually a smaller rover's body, but once we adapted the excavator and added the wheels, so we actually noticed it was actually way bigger than initially thought. So during this process, we decided to take the different approach of extending the dimensions that did not exceed 5 feet and like explaining the length and 4.5 feet in width. The reason for this is because it wouldn't be able to hold its own weight if it was bigger than the standard parameters, and also would not be able to do his function in the best in the best mode, since a bigger rover actually will require more maintenance, more control, more power, and even so will be actually more expensive to build. Thank goodness, since we kept the measurements to less than the established amount, so actually it helped us to prove that it could move and it could actually do the operation. For the third MOP, we'll be going mainly for that is able to hold its own weight and up to 100 pounds. The tools that we'll be using will be the CAD drawings and SolidWorks simulations. First, we'll be selecting the desired parts to calculate the mass on the software. It will give us the overall mass of the rover, and after we calculate that, we'll be actually running the simulation to apply the desired force on the equipment. This actually will show us in the different parts of the rover that forces could be applied and mass that could be applied later on. For example, when it picks up the rec lift, when it gets Let's say we had to add something more in a compensation or something, that we taken into account that if something breaks or something needs to be replaced, even if the replacement is a little heavier than the previous one, it won't affect the rover's internal body. Meaning that it will not collapse on itself. So when we run the simulation, our desired force on the equipment, so it shows no deflection of the structure or the least amount of deflection, that it won't impede the movement of the rover or the main body, so it won't collapse on itself. Then, like previously said, we said we're going to be using SolidWorks simulation to run this. This software actually is proving to be very useful in this presentation, since we can build a physical model because of the limitations in the budget. And since this one actually helps us apply the different materials, the different forces, and even the vibrations it can actually be subjected to, it helps us actually get a better understanding of how the rover will hold up in our tests during the simulations. For the thermal P will be that the structure must be made of the aluminum 6061, which previously stated is the NASA recommended material for most of this built stuff, be rover, even parts of the rockets. This actually is one of the standard materials we'll be using. To actually to validate this result, we'll be going through the CAD drawings and the SolidWorks simulations. Mostly we'll be selecting the desired structural parts to apply the aluminum, which will be the main body part, will not be, for example, the excavator, will not be the fuse box. Those will be the main body part that will be consistent of the main structure that will be holding everything. So we'll be selecting those in aluminum 6061 material. We'll be running a simulation to determine if the material has any effect whatsoever with the other components and the weldings on the rover, since aluminum tends to be a little difficult to work for welding. But since aluminum 6061 has a pretty high resistance, it's not corrosive, and it's also not subject to any treatment of anodized, it recommended to use the welding and between 150 Celsius to 200 Celsius, which is actually pretty reasonable concerning this aluminum. This temperature actually could melt other types of aluminum. And then we'll be actually recording the results of the desired parameters and assemble the parts via welding. Here we presented like the pictures we'll be using, the material we'll be selecting, the SolidWorks, and the main parameters of this material that we'll be using, and the selection in SolidWorks to run the simulations and actually help us validate that this material will work with the rover and give it the enough so it won't collapse on itself or even be susceptible to the vibration that when it's moved or the passage time of corrosion. For the fourth MOP will be the wheel arrangement design that will be designed for rough terrain and to prevent loss of balance when excavating. Here we'll be using the CAD drawings, the SolidWorks, and the visual aid that we'll be using with the simulation. And we'll first verify the drawings, specifications, and material integration. Like a lot of the wheels, sometimes they're made of PVC or aluminum 6061. This actually, the interior rim is aluminum 6061 alloy to help strengthen the main parts of the wheel. And we'll be using less material. It will be a little bit of it will be actually part of aluminum, the spikes that will help when the rover is moving. It will actually keep the rover from tippling over, going through rough terrain. And when we actually decide to start the excavation, the wheels itself, since they're built with these spikes, will be maintaining the area so the rover can do the operation without affecting the movement of and going back or forward, which could affect the gathering of the regolith. The second procedure will be applying the forces through the tire via the simulation to show that the tire will not be subjected to deflation or anything else that could be that the robot could have, that it will be able to maintain the weight. It will be able to move thanks to the motor that we'll be using, and even will be actually help us in the rover in case, for example, the wheel gets damaged, the wheel can keep going without being replaced immediately. And finally, will be record the results and show the model in SolidWorks like we have in the picture right here to help provide that better understanding of how the wheel works and even how it actually helps the rover to move in terrains that would need more horsepower evenly. This design actually for a wheel that would not have the spikes, it will require more torque to move in irregular terrain. But thanks to this design, it requires less torque, which is a less it consumes less voltage and even doesn't exert that much power in the motors.
In this MOP, we're going and how it is that we're going to validate it and or verify it is simply a matter of taking into account how it is that we're going to put it all together once everything is properly or physically manufactured. As explained before, seeing as our only means of verifying and validating this particular capstone is through the means of simulation and observation and calculation, we have no way of proving this physically or constructing it physically. The best that can be done is to take the individual measurements of every electromechanical component that goes into the cable box with the accounting of the cables themselves in questions of gauges and girths and see how much of the cable box can these electrical components can fit in there. As it stands right now, and for the rough gross estimations that we have made thus far without any particular specifications, we deduce that the size of the cable box as designed in the previous phases is enough to hold each individual electromechanical component, such as the controllers, the sensors, cable work of any kind, and other such appendages or attachments that will be required to be in the cable box for easy use and access to the operator. This will be further evidence later down the line, but how it is that we're going to go about it, if and only if this could be handled and produced physically, it would be as follows. In is Basing ourselves off of the SolidWorks design, it would go as in the following fashion: to arrange the controller components in a parallel adjacent to each other to maximize cable box space. That is to say, to simply allocate each individual component in such a way that you can easily access its control panel, its control panel or control face that carries with it the buttons of necessary articulation or necessary activation and so on and so forth. Secondly, would be to properly attach the components via screws, bolts to the cable box back. Of course, simply put, that this is just to attach every component to where it is that we want to arrange them in. The missing procedure in order for this to be accomplished is to allocate the precise drilling holes that need to be placed in the cable box in order for it to, of course, be for the components to be placed in. And it's simply just a matter of choosing the right location and spacing them out adequately. Thirdly, would be to connect controller modules in a cascade fashion, as explained in previous phases, to them connect them individually to the servo motors. As I explained before, the servo motors need to be used as a hive mind, so to speak, in which we have one dominating controller that controls another two individual PID controllers. Those PID controllers, one of them can and will be attached to four individual PID controllers that then in turn will be connected to four individual servo motors. These servo motors will drive our wheels and will be the main functionality of the main movement of the rover. And as for the other PID controller, which is the conveyor's PID controller, will handle both the linear action controller and the independent the individual, sorry, servo motor that controls the action of rotation of the conveyor. And fourthly, we have to connect the secondary electromechanical components such as the surveillance camera, the linear actuator, and so on and so forth. Any other electromechanical device, of course, taken into account, but later will be shown. But as more so than that, would also be in back to the cable box itself would be the small electrical components as explained in phase C2, where we have something like transistors or things like decouplers or recouplers that type of small electrical component that helps that allows for better flow of electricity throughout the electrical motherboard, so to speak. Fifth and finally would be to fasten every electronic component tightly. That is to say, we do not want loose connections for poor electrical signal. We don't want to overcompensate by sending in more power into a potentially open-ended electrical wiring fitting, where possibly there could be something like a fire or something of a electrical fire or something of smoke hazard or just damage to the electrical components whatsoever. With this, we can properly validate and verify the this particular MOP. And moreover, to explain the proper way of doing so, not only is by design but also by visual appreciation or visual confirmation. This would take, if done, once again, if done physically, would be to take everything as explained just now and to verify it once it's going into the particular steps of calibration, which is vital for this particular capstone. Seeing as it's mainly going to be validated through simulation, then there's no particular way of going about it. But if it were to be physically validated, it would be as presented here. In this MOP and how it is that we're going to validate and or verify it, it is a simple matter of electrical accounting analysis. What this refers to and how it is that we're going to go about it is with an electrical accounting calculation. More so to the point, is going to be a theoretical, hand-drawn, or possibly computer calculated assessment and accounting of electrical wattages or voltages, amperages, and overall energy consumption of the main power cell battery. That as of this point, because we haven't done said electrical accounting, we do not precisely know, but have estimated the precise battery bank that's going to be utilized. The cell itself, it has a gross estimate of about 8 inches by 7 inches by 5 inches, and it's going to be a relatively large, but not as large as a car battery cell that's going to power this entire capstone. And how it is that we're going to go about it is as follows. To research each electrical component for power consumption in amperages and voltages, to calculate the wattage usage of a result and summarize it in a result value for each electrical component. To add up all the, as already expressed, to add up all the wattages and of every electrical component in the inventory of the entire rover. That is to say, anything that can pick up electricity will be taken into account, such as the motors themselves, every controller, the surveillance camera, the other actuators, even the sensors themselves. Of course, as the smaller electrical components that they themselves take about, or at least save us at certain occasions, can even save us a certain amount of electrical power by about, let's say, about a 30% for when it comes to the transistors and so on and so forth. Fourthly, we have to multiply and before I continue, this is simply a rule of thumb approach of how it is that we can safely calculate for a power cell battery design. Simply put, we're going to take everything that the rover is going to take up in power, and for how it is that we're going to design the battery is to multiply it by a safety factor, sort of speak. That safety factor being something around 1.5 to anticipate for power supply overload and or let's say overcharge or any type of electrical situation where the power battery can compensate for the amount of power usage and throughout all the components. Fifth, we have to compare the power supply battery cell maximum voltage output to this new calculation, and from which for when we have it to analyze the usage of which, if it is that we're going to do this physically. In this particular case, we have no physical way of assessing all of these. The only way to really go about it in this particular case would be to analyze real life servo motors at various speeds and use the calculation that best fits our particular rover with the target set velocity that as of right now has not been set, but it can be calculated, can be searched for, researched for, and to appropriately account for the wattage, amperages, and voltage usage of said servo motors, which, in all honesty, is going to be the biggest drain on the battery cell itself. And six would be to adjust motor consumption rates to optimize overall battery life. This is where essentially our control program comes into play, or at least how it is that the calibration of the PID controllers comes into play. Because with this, we can set the amount of speed that we want from the motors themselves, to then later adjust whatever amperage or voltage usage that this will take, and will affect the longevity, the life expectancy of our battery, which in turn will of course affect how long we can have this entire rover on the field, at what distances, so on and so forth, and the overall performance of the vehicle, and once again, for how long it is that the operator can actually use this uh, efficiently and safely.
This MOP validation is for the conveyor excavating system. The MOP is that the excavator tool will have 6 to 10 spoons for excavating. It does not have any safety precautions that we need to take. The tools for this would be SolidWorks 3D modeling. This MOP was verified in phase C1, and the procedure is that for the validation we'll have to use the design made in SolidWorks for phase 1. The second MOP bucket should hold at least 10 kilograms of the substance it's recollecting. The tool would be SolidWorks simulation, and the procedure would be to utilize SolidWorks to simulate particles that would act as the gather material. Place the particles in the bucket container and then run the test simulations to see if the bucket at hand that we have now is able to resist the weight of the 10 kilograms of the substance that we are recollecting. This is the most important MOP because this is the one that it's the objective of the mission of the capstone. That the excavator unit must accomplish its mission of recollecting the regolith in 2 minutes or less. The tools will be SolidWorks simulation, and the procedure is to assemble all 3 component subsystems and then run the excavating simulation with all parameters applied. Take note of the simulation results and verify the system to see if it accomplishes its. Since the conveyor will be working with 2 alloy chains, steel alloy chains, we find it necessary that we needed to install a chain tension system to the conveyor as for it to work properly when excavating. For the tools to validate this MOP would be CAD drawing and SolidWorks, and the procedure would be to simulate the chain in SolidWorks without the tension system and then with it to validate its functionality. In order to evade making the conveyor system too bulky or heavy, some of the tool's major components for excavating will be made from durable materials such as aluminum 6061. For the tool, we'll have the CAD drawings and SolidWorks. This MOP was verified during the individual designing of all parts of the conveyor system in phase 1, but will be validated in our next presentation in phase